Hi everyone, welcome to Astronomy on Tap in the Triangle. This is going to be our first virtual event, as you know, and we're so glad that you're all here. We hope you're staying healthy and well during these challenging times, and we're really looking forward to seeing you back at full steam in the fall, we hope. But in the meantime, we have a great talk planned tonight, and I'm going to go ahead and get started with a short introduction talk before handing it over to our speaker. Let me pull up my slides. All right, so tonight we're going to be hearing from Dr. Amy Nicholson, who is a UNC professor, theoretical nuclear physics. And I just want to start off by saying a few things to sort of warm you up for the night. And the first thing I already posted in the chat, which is non-science related, is that full steam, so we're going through some challenging times, and full steam's employees could really use some help right now. So they have this GoFundMe going, Join the Wall, awesome. And if you donate here, it goes all towards the employees, none of towards the business cost. And so please considering doing this. They've been a gracious host to us over the last few years, and they could really use your help so as we can keep going in the fall. But the first science thing I actually wanted to discuss is just to recognize the scale of things that we have in the universe, and that the processes and ingredients that drive the evolution of the universe have such an unimaginable range. You start with things as small as atoms and smaller, which are a billionth of a centimeter, as you go up through planets and stars that are huge compared to us, but are still tiny compared to the size of the universe at about 1 billion centimeters. And you can even go up to the size of galaxies, which is 10 to the 23 centimeters, 10 to the 26 centimeters for clusters and filaments. And so the range of scales that you have is actually, if you're familiar with physics terms, that's actually about 35 orders of magnitude, which is crazy. So the question that a lot of scientists are thinking about is, what are the processes that can take these, the fundamental laws that drive the physics of small things that create large structures in the end, and how are these different scales related? And in terms of stars, one of the key things you should know is that there's basically two forces that play in what holds a star up. The first is gravity, right? So a star is very massive, so the gravity is trying to pull it back in on itself. But as you pull a star in, you actually cause fusion to happen, and that releases radiation pressure that can help support the star from the inside out. And that's driven by a myriad of small reactions with particles like protons, things like that. And these small particles follow what's called in physics the standard model of particle physics. And this basically boils down to there being about 17 fundamental particles, which everything is made of. Some of these you will have learned about in high school, like electrons, things like that. But other things you may have learned about in chemistry, like protons, would actually be decomposed into even smaller fundamental particles like quarks. So with all these particles, they follow 4 fundamental forces, each of which are very important in astronomy. Obviously, gravitation is very important in astronomy because it controls orbits, it controls motion, it controls heating, gravitational heating, and that kind of thing. We have the electromagnetic force, which controls magnetic fields inside galaxies, or the motion of charges inside interstellar gas, things like that. And then we have the weak and strong nuclear forces, which you're going to hear a little bit more about tonight from Dr. Nicholson. But all of these forces are fundamental laws that control small particles, and these laws eventually are what are able to sum up and create physical processes that build the enormous structures we see in the universe, which are stars, planets, galaxies, clusters, and things like that. So with that, I would like to hand it over to Dr. Nicholson. So she's going to tell us a little bit tonight about from quarks to stars, understanding the strong nuclear force. And just to give you a little bit of background, Dr. Nicholson received her BS from New York University and a PhD from the University of Washington. After that, she did 2 postdoctoral fellowships, one at the University of Maryland and the other at the University of California at Berkeley. and she has been an assistant professor at UNC-Chapel Hill since 2017. So I'd like to go ahead and hand it over to her.
Thank you, Zach. All right, can I share my screen? Oh, you need to enable me to share.
Try it now. Thank you.
All righty. So thank you for the introduction. I'm very happy to be here tonight, even though I'm not getting the free beer that was promised to me, but don't worry, I have one, I'm good. So tonight we are going to be learning a bit about the strong nuclear force, which is the thing that holds the nuclei inside of atoms together such that you can create matter. So to begin, this is a public talk, so I'm gonna try to give as many kind of broad details as I can without getting into super technical things. So the first question, we're talking about matter. What is matter? Typically, historically, what's been taken is a top-down approach to understanding matter. So we have some chunk of matter in the universe that we want to understand, like a star. And so we look deeper to see what the star is made up of. And we see that all of the matter inside the star is made up of atoms. Hopefully this is something you've seen in your science classes in high school. And the atoms are composed of positively charged nuclei and are surrounded by negatively charged electrons such that the whole thing is electrically neutral. So we can dig down even farther and we can look inside the atom, and here we see the atomic nucleus itself. And the atomic nucleus is in turn composed of things called protons and neutrons. These protons and neutrons are bound states of even smaller, more fundamental particles called quarks. So if we look inside a single proton, we see that it's in fact made up of even smaller components. And so the way history went, it started with the big stuff that we could see, and then we looked at smaller and smaller distance scales to try to see what is the fundamental thing making up this stuff. And as far as we know right now, at the level of quarks, which are the subatomic particles that make up the standard model, this is as far down as we've gone in our distance. We may need to go farther than that. You can go into things like string theory to look at what might be composing the quarks, but for now, we're gonna assume that these are some fundamental constituents of matter. So what I do in my research is I turn this upside down. So I instead want to take a bottom-up approach. I know that everything is made up of these quarks, and I know the theory behind the quarks, the thing that tells me how they interact with each other and how they bind up to form larger structure. And so I can follow this the other direction and try to start from this theory of the quarks and learn about matter by going step by step the other direction.
Hey, Amy?
Yep.
On your screen, I think there might be a build order window in Zoom over your PowerPoint. Could you just check if that's the case?
Yeah, is it not showing full screen?
No, it was. That was just in the way.
Oh, okay.
I think it's fixed now. Yeah.
Okay.
Thank you.
Thank you. All right. Okay, given that we understand the theory that tells us about these very small distance scales, what are some of the questions we might be able to ask that might be answered using this theory? So these are kind of some of the big questions that I'd like to answer with my research. So the first one is nucleosynthesis. Now, I am not an astronomer, but a lot of the kind of physical systems of interest that I'm interested in looking at are things like stars and what happens after the Big Bang, such things like that. So nucleosynthesis, this is how nuclei are formed from the smaller constituents, is usually driven by fusion within stars. It was also driven by the Big Bang, but I won't go into that in this talk right now. So the simplest kind of stellar fusion that we know about is the fusion that goes on inside our star. And this is called a PP chain. And this is what actually causes our star to burn. So essentially what happens is after the Big Bang, you have a whole bunch of hydrogen laying around. Gravity tends to pull it together. And once it gets close enough, then you can have the protons that are inside of hydrogen gas fuse together to form some heavier nucleus. So the first step in this chain is the deuteron, which is composed of just a proton and a neutron. And when these two fuse together, they produce energy. So this is why nuclear fusion is a kind of promising avenue for looking for types of energy that we could use to run everything, electricity in our houses, et cetera. And then the chain continues. You have more protons running around in hydrogen gas, and eventually the end of the line is you form helium-4, and you end up with 2 protons left over that can then go off and start the chain again. Now, what can we learn about this? So we know a lot about it based on observations of things that happen in the sun. But one thing that we know theoretically is that this whole picture is very, very sensitive to a particular quantity. This quantity is called the binding energy of the deuteron, which is this bound state of protons and neutrons. And the binding energy is something that characterizes how tightly bound they are together. And therefore, it determines the rates at which these reactions occur and how much energy is produced, et cetera. And so this is what we know that the binding energy of the deuteron is. It's in units of MeV. Don't worry about that. Those are fancy units that we use. We're only going to ever be comparing different numbers to each other. So the binding energy of deuteron is about 2 within this system of units here. So why is that interesting? Oops. There we go. So what's interesting about it is it seems to be a very finely tuned quantity. So 2.2 MeV is a very small number when you compare it to the binding energies of every other atomic nucleus in the universe. It's much smaller than all other nuclei. And so the question is this by chance? Is it just that nature chose some numbers and they came together and out came the binding energy of the deuteron? Is it necessary? Is it built into the theory in some more natural way? And the reason why this is an interesting question is because this very precise number that we know right here, if it wasn't this number, if it was something different, then we wouldn't be able to have a slow burning sun like we do today and like we need for having life on a planet. So a question that I can ask as a theorist is how much can I tweak these fundamental parameters of the universe and still have a slow burning sun that allows for life to evolve on Earth? So moving farther down the chain, at the end of that previous line, we ended up with a whole bunch of helium in our stars. So eventually all of the hydrogen burns off. We're left with a whole bunch of helium, and now we can take helium and fuse them together to form even heavier nuclei. So this is the chain that is used in stars to produce carbon-12, which is obviously very important because we need carbon-12 in order to have life. It's the structure behind basically what makes up our cellular structures. So how does this happen? 2 heliums fuse together. Again, they produce energy. This keeps the star burning. They form beryllium-8, and then beryllium-8 has to capture another helium-4 in order to produce carbon-12. So the problem with this is that at face value, this process is very, very unlikely to ever happen. Essentially, you have to have 3 helium nuclei at the same exact point in space in order for this carbon-12 to form. And if you just look at the way normal nuclei interact and how they fuse together, this shouldn't happen. And so it was posited by a scientist named Hoyle. Oh, yes, also, yes, you were created in a star, so you can tell your friends that. You're pretty cool. So Hoyle said, well, okay, there must be something else going on that enhances this process enough that we produce enough carbon that we can produce life in the universe. And so he said there must be something called a resonance. Okay, so what's a resonance? A a resonance is basically just an enhancement of a process. So the typical example that you would give is if you think of having a wine glass and an opera singer, and the singer hits a very particular note, and that causes the vibrations inside the glass to amplify so much that the glass explodes. So that's called a resonance. It happens at a very particular frequency. So in particle physics, we have similar ideas where if we have states that are occurring at a very particular energy, then the processes are greatly enhanced. They happen much, much more often. And so Hoyle said there must be a resonance in this process here where beryllium-8 captures helium-4 in order to have the abundance of carbon that we have. And indeed, experimentalists went and they looked for this resonance and they found it. So you could ask the same question. This is even more finely tuned. So this resonance, does it occur at just the right energy? Because if it didn't, then we wouldn't have enough carbon in the universe to have life, and therefore we couldn't be here to ask this question. That's kind of not the way physicists like to think about it because you can't really test it. And so what we would really like to find is that, no, it's actually something that's more fundamentally built into the theory and not just some random coincidence of parameters that leads to these things. Okay, and then the second type of question that I'm going to be talking about is what happens to matter under extreme conditions. So in particular, these extreme conditions come about through stellar evolution. So we talked a little bit about where our sun is in this fusion process. It's largely hydrogen, fuses to helium. But then in older stars where you have lots of helium around, you have this other chain where you produce carbon. And so you can talk about how these stars will evolve as they go on in time. And as Zach already mentioned, there are some competing forces in the evolution of these stars. We have gravity, which tends to want to pull all of matter in toward the center, so it wants to collapse everything in. And on the other hand, we have heat or energy, or thermal pressure is what we would call it. And this heat energy tends to make things want to expand. So you can think of it like I have a pot of water, I apply heat to it, and it turns into steam, which fills the room, so it expands. Another way you might think about it, if you have a bunch of bored kids at home, they're quarantined, they have nowhere to go, and you apply sugar, which is another form of energy, then suddenly they fill the house, eventually breaking out of windows and spilling out onto the street, and they expand in that way. I don't actually have children, but this is how I view parenting. All right, so now that we understand the forces that we have on stars as they evolve, we can look at a couple of different evolution paths. So one is a little bit more boring path. This is the path that our sun would take. So it uses these fusion processes, which creates energy. It causes it to burn. That creates this thermal pressure that wants to keep the matter away from the center. So it grows, and eventually it loses fuel, and the matter kind of all disperses out into space, and you end up with something called a white dwarf. Kind of the more interesting and dynamic path that a star can take. If you have a much larger star, maybe 8 times as big as our sun, then it will follow a similar path. It'll go through fusion, it'll get bigger and bigger until all of a sudden it runs out of fuel. So it no longer has anything that can fuse together in order to create this heat energy that keeps it from collapsing. And now suddenly gravity takes over very, very quickly. So all of a sudden you run out of fuel, boom, all of the matter wants to crash in toward the center caused by gravity. And when you do that, you create a shock wave, which is essentially an explosion that causes all of the matter to now go flying out into space. And this is called a supernova. And what's left over at the end of the supernova is one of 2 things. If you have a very, very massive star, then all of the matter in the center of the supernova will collapse in on itself and produce a black hole. On the other hand, if you have just enough mass that it goes through a supernova, but not enough that it creates a black hole, then what you're left with is a lump of neutrons, which are very, very cold out in space. And this is something called a neutron star. Kind of crazy. Basically, at this point, the only thing keeping it from collapsing in due to gravity is quantum mechanics. So these big scales and these small scales are really both at play in something that we call a neutron star. So you can think of a neutron star as representing the most dense that you can make matter before it collapses into a black hole. So this is the most dense matter in the universe. How dense is it? There are lots of different cute comparisons out there. My favorite is if you had a teaspoon of its material, then the mass of that material would be over 900 times that of the Great Pyramid of Giza. So we're talking massive amounts of mass that we have constricted into a very small space. So what happens when you compress matter to its very limit? This is something we cannot recreate on Earth. We can't recreate the what's going on inside a supernova here on Earth. And so all we can do is infer based on observations what might be happening, or we can theorize based on our theories what could be going on. So if you do a Google image search for a neutron star, you come up with a variety of different conditions that people guess that might be happening. There are some really interesting theories that people come up with, mostly for the outer layers of the neutron star, which are not as dense. The core, the very middle, is going to be the very densest because that's where gravity is the strongest. So my favorites are the so-called pasta phases. You have a spaghetti phase, a fettuccine phase, a ravioli or a lasagna phase, etc. And then finally you get into the Swiss cheese phase. I think this is just evidence that we need to give astronomers sandwiches because they're hungry. But again, a lot of work has been put into this, into trying to guess what kind of form matter might take. But the overarching thing that you see in all of these pictures is that at the very middle, everyone has a question mark. Nobody really has any idea what is going on inside the very densest core of these stars. So that's where I think it would be really cool to start to understand what's going on there. And so, like I said, it's really hard to learn about what's going on in these stars, but there is some promising new developments. An experimental collaboration, LIGO, recently detected what are called gravitational waves, and gravitational waves are ripples in space-time that propagate throughout the universe until they hit a detector. And these gravitational waves are created when two of these neutron stars collided with each other. And so by measuring the properties of the ripples in space-time that came out of this, we can try to infer what must have been happening in the middle of these stars before that collision. All right, so let's now move on to theory. So these are some of the big questions that I'd like to answer. So now I'm going to tell you about what the theory is that I use to answer these questions. So again, Zach already pointed this out in the beginning. We have a standard model. It is the standard model of particle physics. And it tells us about all the different particles that we know of, that we've discovered. And it also tells us about their interactions. So these are the particles out here. These are also particles, but these are very particular kinds of particles. They mediate the different forces. So the photon mediates the force of electricity and magnetism between particles, etc. And then the Higgs boson, which hopefully you've heard about in the popular press. The Higgs boson gives mass to all of the different particles that couple to it. So to break it down a little bit, we talked about everyday matter. That's what we want to study. And everyday matter is composed of only a subset of these particles. You have the up and down quarks. You have the electron, the photon, and then the gluon. And the gluon is the thing that mediates the force between the quarks. I'll talk a little bit more about that. Now, QCD, which is my research area, studies both the things that are in fundamental matter, but also a few other more interesting things, equally but differently interesting. So I study all of the quarks, not just the up and down, but also the oddly named charm, top, strange, and bottom. And the gluon, which is the force-carrying particle that tells you how these guys interact. All right, so I'm a theorist. I need to have at least one equation on my slides or they will throw me out of the theorist club. So this is quantum chromodynamics, or QCD. This is the theory that I study. It is a subset of the full standard model. And it's given by this one equation here. Now, we're not going to solve this. There won't be a test at the end, so don't worry about it. But we are going to talk a little bit about what the ingredients are of this equation. So quantum, it's a quantum theory. We have to use quantum mechanics to describe these things. They're very small. Dynamics tells us how they move and interact. And then the word chromo is the one that's particular to QCD. And chromo, as we know, stands for color. And so the reason why it's quantum chromodynamics is that quarks and gluons carry a color. Okay, I put color in quotes. It's not a real color. It's not like if you were to pick up a quark and look at it under a microscope, you would see that it's red. Really, you should think of it just as a different type. So you have red, blue, and green type of quarks. And nature in particular likes to combine these in order to form colorless objects. So what do I mean by colorless? So the quarks bind together to form the proton and the neutron, and they always bind together in groups of 3. You always have one red, blue, and green quark, because together those 3 colors make white. So the proton is considered white or a colorless object. Same with the neutron. And we see no free quarks in nature. Everything that we see are things like protons and neutrons, which are overall colorless objects. We only know that there must be smaller constituent particles because we can perform experiments where, say, we shoot something at very high energy into the proton and it interacts with an individual quark, and from that we infer that there is some smaller structure, but we can't actually produce a single quark in a lab. The gluons are the particles that hold them all together. So how do these things bind together? Well, through glue, hence the name. Quarks also have what's called flavor. When I talk about the flavor, I'm talking about these different labels here, the up, charm, top, down, strange, and bottom. Those are the 6 different flavors. They essentially all have different masses. So again, this is not real flavor. If you were to lick a quark, it would not taste different from a different one. And I apologize for these names, but it was the 60s, so not my fault. All right, so the next thing we want to talk about are those masses. The different flavors have different masses. Where do they get these masses and why are they different? So hopefully a lot of you have heard about the Higgs boson. It's been in the news a lot because it was recently discovered at CERN. And so we know that it's via something called the Higgs mechanism that the quarks get their masses. And we know from measurements that the mass of the up quark is very small, it's about 2 MeV. The mass of the down quark is about 5 MeV. So we can look at something which is a constituent, which is a bound state of different types of quarks, like the proton. So here, the proton, we know we have to have 3 of them, such that we have red, blue, and green forming a colorless object. And the proton has 2 ups and 1 down. So I can take 4 MeV from the 2 U quarks and 5 MeV from the down quark, and I can add them together to give me the mass of the proton. Except there's a problem. So we know from experiment, from measurements, that the mass of the proton is huge compared to 9 MeV, which is what you would predict by just summing these quark masses. And in fact, as a theorist, I'm able to take the Higgs field and I can dial its strength either up or down, or I can completely turn it off from my theory. And I can say, what happens if I get rid of the Higgs entirely so that none of the particles pick up mass from this Higgs boson? What happens to the proton? And you find that when you do this, the proton still has a mass of 900 MeV. So very close to what it is in nature. So clearly the Higgs is not what's giving the mass to the proton or the neutron or any other larger constituent of matter. So what's going on? Well, this simple picture of just having 3 quarks is not good enough. What actually happens is, like I said, there is a sea of glue that binds these things together, and also some more quarks running around. And to bind these things together, they have to have energy inside them. And as we know, E equals mc squared. So if you have energy that is keeping these quarks together, then that can be interpreted as a mass for the proton. So essentially 95% of the mass of the proton actually comes from QCD energy and not from the Higgs at all. There's a famous cartoon of the Higgs mechanism, which lots of people like to show, which tells how the Higgs gives mass to these things. And so the story is, okay, the Higgs is a field, it exists through all of space, and it's uniformly distributed. So these people are uniformly distributed throughout space. And then some famous person comes in, which we can think of as a particle, and his fans gather around him and they slow his progress through the room because they're all trying to get autographs. And so essentially they give him some inertia. It's like he's become very heavy because in order to continue moving through the room, he has to carry along with him all these people gathering around him. But as a QCD theorist, I just told you that 95% of the mass of the things that actually make up the matter that we see doesn't come from the Higgs. This is my picture of the Higgs mechanism. So it's as if you have QCD creating this giant whale, and it's moving through a Higgs sea of these little tiny fishies. And every now and again, the whale will eat a fish, and yes, its mass will increase, but it's not a very large effect. Okay, so we've now talked about all the different parts of QCD. I wrote it down. It's this very simple form here. Let's go ahead and solve it, and let's see if we can calculate something simple like the mass of the proton. So what is that energy that is keeping it together to give it this heavy mass? There's a problem there too. Okay, if there wasn't a problem, then I would be out of a job because somebody would have already solved this decades ago, and I wouldn't still be around talking about it. So you may have heard of the Clay Mathematical Institute. They put out a series of so-called millennium problems, which are considered the most difficult problems, but most important problems to be solved. And currently this one is unsolved. So this one is called Yang-Mills and the mass gap. This is exactly the calculation that I just talked about. Can you calculate the mass of the proton starting from QCD? But if you guys can solve it, you'll get $1 million. So by all means, get to work. So if we can't solve it, it's too hard. What do? We don't give up. We resort instead to numerical calculations. So lattice QCD is my field, and it's essentially taking QCD, which is too hard to solve on pencil and paper, and putting it into a computer and letting the computer solve. Even that is very, very difficult to do. Lattice QCD was formulated in the 80s by Ken Wilson, who is also a Nobel Prize winner. And the reason it's difficult is that QCD does not fit in a computer. I can't just type that equation in, hit enter, and out comes an answer. So what's the issue? So first off, we take the thing that we want to study, which is the universe, okay? And I say, all right, I want to study this. What tools do I have? And a problem that you come up against is saying, okay, I can study the universe at this scale from far away. I have lots and lots of stars here, but what if I wanted to see something that's happening inside a single star? Or what if I wanted to see what's happening inside a single atom inside a star, or a single quark inside a star, et cetera? You can keep going to smaller and smaller distances. That's like resolving this picture to infinite precision. To do that, you would have to have an infinite number of pixels in your computer in order to render this to infinite resolution. So we can't do that. So the first thing we do is we take space and time that our universe lives in and we pixelate it. So we set a shortest distance scale at which we can actually resolve what we want to learn about. And so that takes this infinite resolution that we started with and it makes it finite. The next thing we have to do, we still can't fit the whole universe inside a computer, so we truncate it. We want to look at only a small patch of the universe. So now I've taken what was an infinite problem, and it's a finite problem where it's basically just the number of pixels that are inside this picture. I also have to do something a little crazy. We take time and we go to what's called imaginary time. You might ask why. Well, my answer is I'm a theorist and I can do what I want. But really, it's just a mathematical trick that allows you to use the normal computers that we have to get observables. It's also where unicorns live, so I think that's a definite plus. So now I've taken my problem, I've made it finite. Can I now just put it on a computer and calculate? And the answer is no. I've made my problem finite, but it is still much, much too large to fit inside any computer you can come up with, even the largest supercomputers in the world, which are the computers that I run on. So the last step is, instead of trying to understand everything, what we do is we use Monte Carlo methods, so-called because it's like rolling the dice. You're picking random configurations that space and time can take on at any given moment, instead of looking at all possible space and time configurations. And then I insert mathematical probes, like putting quarks inside this sea of gluons that are going on, and I can measure interactions. So that is lattice QCD in a nutshell. And as I said, lattice QCD was formulated roughly in the 80s. It's been around for a very, very long time, but we've only now reached a stage where we can actually start producing precision calculations from lattice QCD. So this was kind of a seminal calculation, but it wasn't that long ago, 2015, by the German collaboration, the BMW collaboration. All right, so what about nuclear physics? I'm interested in nuclear physics. I want to understand questions that come up in nuclear physics. So does lattice QCD work for that? We know that it works fine for a single proton or neutron, but what if we want to have multiple ones that bind together to form nuclei? The simplest observable you can think of to calculate is called the nucleon axial charge, or GA. It governs many, many different processes in nuclear physics, particularly nuclear beta decay, so how nuclei undergo decay into smaller nuclei. It governs the force between protons and neutrons inside a nucleus. Big Bang nucleosynthesis depends very sensitively on it. Stellar processes like this PP fusion in the sun depends very heavily on this quantity GA. So this is the simplest thing we can think of. And this is the current status of kind of everyone in the world trying to calculate this quantity. So this is the value for this quantity GA versus time. And by time, I mean actual time versus year of calculation. So people have been trying to calculate this using lattice QCD for a long time. This red line here is the experimentally known value for GA, and the width is the uncertainty on the experiments. And then each data point is a different lattice calculation by a different lattice collaboration. There are many of them around the world. And each of these calculations takes years to do. So each data point has taken several physicists years in order to come up with. And the most obvious thing you can see is that we're kind of doing a crappy job. So experiment has a number up here. It's very, very precise. And the theory numbers are kind of all over the place. They tend to be very low compared to that. And also they have huge uncertainties associated with them compared to the experiment. And all this is to say that nuclear physics on the lattice is hard, but we will persevere. So kind of a big mind shift that had to happen was, we're not just going to keep getting bigger and bigger computers. We can't just keep attacking the problem in the same way. We're going to have to come up with new theoretical tools that will let us do a better calculation with the computers we have now. And so that's what my group did. If you'll notice, these 2 points here are much, much closer to the experimental value and have significantly smaller error bars or uncertainties compared to all the other groups. And we did this by coming up with an entirely new theoretical formulation for how we extract this number. And this was published in 2018. And not so humble brag, when I like looking at this plot, is seeing that even the groups who started calculating after we put out these results, they're still nowhere near to catching up where we are right now. But the big takeaway from this is that over many decades, we have finally reached a level of precision for at least this one quantity in nuclear physics. Okay, so the method works. Maybe not so interesting because we know this value from experiment. What we really want to know is, can theory do something that experiment can't? So another thing that I want to talk about that we can measure is the force between two neutrons or protons. So essentially in my calculation, I take my sea of gluons and quarks, and I stick in not just 3 quarks for 1 neutron or proton, but I stick in 6 quarks, which have 2 neutrons or protons, and I measure what happens in there. This can also be measured experimentally through a totally different process. They take neutrons and protons, they shoot them at each other and collide them, and they see what comes out, and from that they can infer what the force must have been between them. So that's not so interesting. We want to do something totally new that experiment can't do. So I'm going to go back to the Higgs for a moment here. I said again that the Higgs boson gives mass to the quarks, although not much of the mass of the quarks actually has anything to do with the mass of matter. And I'm going to go even farther for poor Professor Higgs and say, well, even the Higgs boson doesn't give mass to the quarks. In my world, I'm a theorist, and the mass of the quark is just a parameter in my equation, and I can tune it to be whatever I want. So really, I give the mass to the quark to be what I want it to be, and it doesn't have to be what it is in nature. So I can dial the Higgs field to be off, or I can dial the Higgs field to be bigger such that all the particles have even bigger masses. And this is something that experimentalists don't get to do. They're stuck with the masses that are given to them in nature. And so what you can ask is, well, we had all these finely tuned situations that were necessary to have life on Earth. How much can I change the mass of these quarks and still be able to have the universe that we are familiar with? So this is a calculation that I performed with my group. This is looking at forces between neutrons and protons. I don't expect you to understand these graphs because I'm not even going to explain them to you. But basically, we took the mass of the quarks to be about 10 times bigger than they are in nature. And we looked at interactions in various different spatial configurations. You might recognize these from high school chemistry. Just like electrons like to live in specific spatial orientations around an atom, so do the neutrons and protons. And the important part is that the deuteron, which as I said is an important part of the PP chain that fuels our sun, lives here. So I can blow this part up. I've just looked at this small patch of that graph. And the remarkable thing is that when I take the masses of the quarks to be 10 times what they are in nature, I actually find 2 clusters of points indicating that there are 2 deuterons in a world where we have these very heavy quark masses compared to what we have. And so even though I said that the quark masses in the Higgs field have a very small effect on the mass of the proton, it seems that they have a very big effect in the binding of neutrons and protons together into nuclei. And so now I can ask, what are the consequences for fine-tuning in stars, like solar fusion in the Hoyle state? And the answer is we don't know. It could be something way far out there. So this is work in progress, unfortunately. Finally, I talked about neutron stars. We want to know what's happening in the core where the matter is very, very dense. Can we directly put a neutron star on our lattice? The answer is no, it's much too big. But what we can do is we can calculate properties of smaller systems that will give us input into theoretical models for neutron stars. One of the more interesting ones is that theory predicts that as you pile all these up and down quarks very, very closely together, so you're taking your matter and you're squishing it, and matter is composed of up and down quarks. And as you squish them together, they become piled on top of each other more and more. And nature doesn't like this. This is called the Pauli exclusion principle. And so what might happen is that you might start populating your system with heavier quark flavors like the strange quark. And so it's been hypothesized that there might be out there some stars called strange stars, which have a lot of these strange quarks. And these are unstable in ordinary matter, so it's difficult to study experimentally, but we can do it very easily theoretically if I just replace one of my down quarks with an S quark, and I can study interactions like this. And then finally, again, as you start squeezing matter together, then not just neutron-proton forces become important, but 3 neutron forces become important. This is also really hard to measure experimentally. It's hard to shoot 3 neutrons and have them all hit at the same point and scatter, but we can do this with experiment. And this is, again, ongoing work that we're looking at. And then my final spiel that I want to go into now, we talked about the standard model and things we can learn about matter if we understand it. But what lies beyond the standard model? There are lots of things out there that we can't explain with the standard model. And kind of the biggest one might be the so-called matter-antimatter asymmetry. So in addition to matter, there's also something called antimatter. And we don't have a lot of it floating around. All of the matter we know is not antimatter, because when matter and antimatter come together, they annihilate to produce light. And so the standard model itself predicts that shortly after the Big Bang, there would have been equal numbers of matter and antimatter. They all would have annihilated and produced a universe of pure light. There would be no matter at all. And that's what the standard model predicts. That is obviously not what we have. We have matter, we have stars, and we have humans, and all these things that are made out of matter. So why did some of the matter survive after the Big Bang to produce us? And this is one of the big open questions, and this is something I'm also trying to answer. And then finally, I talked about matter, but I was kind of cheating. I was talking about only the ordinary matter that we're used to, which actually composes very little of what the universe is composed of. 85% of the universe is actually made up of what's called dark matter. And it's dark because we can't see it, which makes it very hard for us to understand what the properties are. We do know that it's not made out of those standard model particles. It's not made out of quarks and electrons and all those other things. So it has to be something new. And so what I'm trying to learn about is, what is this dark matter made of? And this is kind of an artist's rendition of what the universe would look like if we could see the dark matter. So these points here are stars, and then all the purple stuff filling it in is the dark matter that we don't see. So many exciting results on the way, and I would like to acknowledge the others in my collaboration. We come from all over the US, mostly, with a few abroad, and again, we run on some of the biggest computers in the world, and so we get a lot of funding in order to do this computing. So, thank you.
Thank you, Amy. That talk was great. So I hope everyone enjoyed that. I learned a lot for sure. Nuclear astronomy and nuclear physics is definitely not my forte, so that was very interesting to hear. And what I'd like to do now is actually go ahead and open it up to questions. So all of you that are watching, you can put your questions in on the chat window. And I think if it's okay with you, Amy, what would be best is for me to just sort of moderate. I can repeat the questions as they come in, and then you can answer them. And actually, we already got one question while you were speaking, so maybe we can start with that. And the first question was from Mr. Mike. And the question was, would a quantum computer help? And the context was with your supercomputer resources not being sufficient to solve the kind of problems that you would ideally want to.
So the question is, how would quantum computers, I missed the beginning of what you said.
Yeah, the question was, would a quantum computer help solve the kinds of problems that you're interested in solving?
Yes, it would help immensely. So a lot of the issues that we have, particularly in scaling up to larger systems. So most of the things I talked about had 1 or 2 or 3 protons and neutrons, and that's limited by computing power. And all of the computing issues that we have are exponential. And so as you make your system size larger, your computational needs grow exponentially. And quantum computers in particular are great for getting around these exponential problems. And actually, a lot of lattice theorists have gone into quantum computing and are starting to formulate these things onto those. So it's out there. Hopefully quantum computers will actually become a real thing soon, a useful thing soon.
Okay, that's awesome. So I'd like to see some more questions come in the chat. I'm not seeing any so far, but there might be a bit of delay. But I had a question in the meantime. So I was pretty fascinated by the topic of strange stars that you're talking about with, different kinds of nuclei that might be in there. And I was wondering if you think, could that be any kind of, not even if it's significant, but could that be a constituent to the dark matter problem, that maybe we don't see those because they don't interact in the normal way that we expect?
So strange quarks actually do interact electromagnetically. So they would interact with photons and produce light. They can't be dark matter. And in particular, any kind of very massive and compact object, like a star, like a brown dwarf or some very small star that's not luminous, they've already ruled those out as being dark matter candidates. They use gravitational lensing, and so they've counted the number of objects that are like that around the universe. And gravitational lensing doesn't rely upon them being luminous. And so that's already been ruled out. So we really know that it's not caused by any standard model particles that are building some large compact objects. It has to be some new particle that is more homogeneous throughout space. That makes sense.
Cool. Very cool. Thank you. So the next question comes from Nathan Gronalds. And the question is, do you have any idea how many qubits would be needed to solve these types of quantum mechanical problems?
I do not. No. Way more than is even reasonable on any time scale that we're talking about. I would say it's definitely not in the next 50 years that we're going to develop a quantum computer that will be able to handle these problems. There is an answer to that question. I just don't know it off the top of my head.
That's okay. Thank you.
People have looked at that.
Okay, we have another question from Josh Redding, and he asks, is there an easy way to explain how the Higgs gives mass to particles?
Yeah, so the easiest way to explain is kind of that cartoon that I went through, where you have some field that exists through all of space, and as particles move through it, they distort it such that the field clumps around those things. So remember that really what we call mass is actually inertia. So something that's more massive has more inertia. If you get hit by a very massive thing, you're going to get more hurt, right? And so it's like the ability to stop a very massive object is what we think of as inertia. And so in this way, as the particles move through this field, they are interacting with the field in such a way that it slows it down as if it had a heavier mass, as if it carried more inertia. So that's kind of the only hand-wavy way that I know to explain that. The physicsy way is you have coupling to a field and there's spontaneous symmetry breaking and cool stuff, but.
Very cool. Thank you.
Mm-hmm.
Do we have any more questions from the audience? Give a moment to see if we have any more come in. All right, well, if there are no more questions, I think that might conclude it for the night. So thank you again, Amy, for giving your talk. I think that was very informative, interesting for everyone. And we'd love to have you back at some point, hopefully when we can all convene again at full steam. I know we're all looking forward to that.
Yeah, it'd be nice to share a beer.
Yeah, definitely.
Drinking by myself. Well, thank you for inviting me. I had a good time.
Oh, can we have one more question? If you have time. So we have a question just come in and said, how does your collaboration get such a low uncertainty on your calculation of G sub A in comparison to other methods?
Yeah, so how can I say that? Okay, so basically everyone who did this calculation before, mostly everyone, used a very particular type of method for extracting the quantity GA from the data that we get coming out of the computer. That's a whole business in and of itself. And the tricky thing about that was they have to perform extrapolations to the physical point. So when we do these lattice calculations, I said that we discretize space and time, we truncate it, we go to imaginary time, all these things which are unphysical. And in the end, to get a physical result, you have to remove all of the stuff that you did to distort the theory. And so you typically have to extrapolate, for example, to zero lattice spacing. So you don't want it to be these discrete pixels, you want to extrapolate away that discretization. And the way that they do this, they have to extrapolate in multiple dimensions, which is very tricky. It's also very tricky to generate the data because you have to generate a lot of data in order to do this extrapolation. And so what we did was we took one of those directions that they had to extrapolate in, and we kind of theoretically summed over it and got rid of it as a free parameter so that we only had to extrapolate in a single variable. And that gives you a much cleaner extraction of the data. It also helps us get around quite a bit these exponential issues that I talked about with needing exponentially larger computers to go to larger system sizes. We kind of got around that by not going into the regime where it's exponentially hard. And so we were able to, with kind of a normal sized allocation of computer time, get a lot more out of the data in that way.
Very cool, thank you. Let's make sure, just give a few more moments to make sure there's no more questions coming in. There's a bit of a delay between what the audience sees and when we speak, so we could just give it a few seconds, that would be good. Okay, well, if there's no more coming in, I think that's all for tonight. Thank you again, Amy, and thank you everyone for coming. We're looking to see everyone back in person at full steam this fall. So thank you for coming out. Thank you for your support, and we'll see you then. Thanks.
Thank you.